Hello guys, so now we're going to start looking at how we can create this effect, and this is the final result that I have. It's the including the final render as well, and this is the reference that I was using, that I got the idea from. And you can see here we have a nuclear explosion happening, and then the first shockwave is what hits this the bus here, and you can see we have a lot of dust being emitted from the surface, and there's a lot of force pushing it from this way, and you can see it's following the surface curvature and everything. So the idea is we want to emit smoke and then have the same kind of force pushes the smoke from left to right, for example, and then see what we get. And then we're going to improve that to add a little bit more interesting details to have the smoke follow the surface. So that was the first impact, and then the second one is much stronger, and we're not going to do that. Cool. So let's see how we're going to do this. And the first thing is we're going to import the geometry. So I have the tank mesh here. Sorry. Tank. And the first thing that we need is we need to prepare the mesh for our sims. And this is a very complex process, and it requires generally a lot of custom modeling or preparation that you need that needs to be done to create an interesting mesh that can work nicely with the sim. For example, you can see there's a lot of fine details, so capturing those will be tricky. And then it will be tricky because of the size of this detail versus, for example, this shape here. And then there is a lot of openings as well. There is this whole interior here is open, and there is holes, and we don't want the volume to be leaking inside the tank and get stuck inside. So we want to make a fully closed shape of this entire mesh. And the easiest method to create something like that is to convert the mesh into a volume, and then from that volume you generate a new mesh. And this method works really well using VDB, so I'm going to try that. I'm going to create a VDB from Polygon, and right now it's creating what we call a surface field. Actually, let me explain this. Let me explain the difference between the surface and the density field. So we have two different types, and you can see this one is represented as a smoke, and this one is displayed similar to what geometry looks like. If I increase the voxel count, it will display it similar to what a surface looks like, an actual geometry surface looks like. I think I've increased the resolution too high, but yeah, this is the volume. You can see now we have a surface representation. Now let me explain what's happening. And I'm gonna draw two voxels. And let's say we have these are the voxel cells. And when we have a volume, let me copy this. When we have a density volume like this, the information is stored at the voxel level. So this is voxel 0 and this is voxel 1. So it will either fill this entire voxel with data, and or it will not. And depending on the resolution that you have, you will end up with stepping, whether you're going to see it because of the voxel size or not. Let me increase this to 1. And you can see it already, there is a stepping effect. And the reason for that is because if the surface, for example, is very fine and it has a lot of details, it's hard to capture those with this 0 to 1 logic. It's hard to display that data unless you make this super small, but the stepping is still there, but it's just not visible. Now with the SDF, it can store more information. It can store how far it is in from the isosurface. So it knows where the limit of the original surface is, and these are 2 voxels. It knows, for example, that the surface is here, and the way it stores that, it stores a negative value when the data is inside the volume. So let's say -0 to here, and it stores a positive value if the data is outside the volume. So for example, here it can store a 0.1, and we know how far inside we are into the SDF, into the science distance field, which is what the surface is meant for. It's basically a science distance field. And by having the ability to use float, we can specify where this surface limit is. We can specify exactly where that is. So the SDF can represent geometry and anything in general much more accurately, so we can get this kind of information. And the reason it can display this is because it can easily create what's called a gradient, which is basically the distance that it takes this point to reach the surface, the isosurface of this volume. And it creates a vector that takes that point from that current location to be at the isosurface, and that's what is used as the gradient. And Houdini is using that to display this volume here as a surface. It uses that to shade the normals, basically. And so with the isosurface, we can represent geometry much more accurately, as you can see here. But now the VDB conversion failed to capture all these guys. You can see this is not a good representation at all. Now let me show the method that we're going to use and try to explain it. What we need is we need to create a geometry that represents the volume of each of these guys. Okay, so for example, I isolated this. I don't care about this part. I only care about creating a geometry that represents this entire volume without considering the cavities. I don't care about those. And the best tool to use for that is called Tidrahilize, and we need to generate what we call a convex mesh. And what a convex mesh is it's going to try and wrap this geometry using another geometry that wraps around it as much as possible, as close as possible to the original representation. So let me plug in a Tidrahilize node, and I'm going to change it to convex hull. Instead of confirm to surface, I'm going to change it to convex hull. And you can see now it created this volume that is filled, and it encapsulates the entire input geometry, the original one. Now let's try it with something else. Let's try it with, with this guy, for example. It doesn't want to select it. Okay, let's try with the wheels. I'm hitting the Shift G key, which grows the selection, but because the mesh is a little bit complex, it takes time. So I'm going to hit enter, and now we have this geometry. Let's copy this and take a look at what we get. Cool, so we get a fully enclosed surface that is very close to the original one. We're losing this detail, but for the collision creation, I don't think it's gonna matter that much unless we have something really close. And we don't have to run this operation on everything. We can run it on the pieces that causes issue, but that will require us to go and start isolating each one of these guys, which I don't want to do. So I want to treat this as a whole. I'm gonna delete this, and we cannot run the Tidrahilize on all the mesh at once. We need to loop over each piece and then create a convex hull for that. So I'm gonna create a connectivity node, and this will give a primitive value for each piece. So if I view the values, you can see each primitive has a unique value based on their grouping, based on the connectivity. And then I'm going to create a for each loop. And we're going to loop over each primitive using the attribute called class. Now if we look here, we should see a single shape, and I'm going to plug in this tetrahedralized node and make sure it's set to convex hull. And now let's wait for it. It's going to loop over all the each piece and create a convex hull. It's almost there. Cool. So now we've finished that process, and you can see the newly created geometry is very close to the original one, but it doesn't have any openings anymore. And this is going to be great for VDB conversion. So I'm going to create a VDB from Polygon. And let's take a look. Trying to compute that. Cool. I'm going to increase the resolution of lower the voxel size to increase the resolution of the volume. Awesome. So you can see we have a very nice volume here, and I'm going to convert that into a mesh again to show you what the new mesh looks like. We can take any volume and convert it into a mesh. And this is the surface that we have. You can see it's fully enclosed. Let's go inside. It doesn't have, I mean, we're not gonna get inside there. So it's fully enclosed, doesn't have any holes or anything. So we're gonna be able to use this nicely with the volume. I can increase the adaptivity of this conversion, so it only keeps the detail where it thinks it's needed. It analyzes the curvature and places the polygon as needed. So I'm going to set that to something higher to have a more efficient mesh. I'm going to call this surface, out surface, and let's see. And then the next thing is we want to use this to emit smoke. So what I'm going to do is I'm going to scatter some points. Let's increase the number of points. And then I'm going to use these points to create a fluid emitter, a smoke emitter. So I'm going to create a fluid source node, which is what we generally use to prepare any data for DOPs, for sourcing for DOPs. And I'm going to select the node and then go under the container settings and make sure it's set to smoke. Sometimes because even if it's set here to initialize to the default, sometimes it doesn't have all the settings set correctly. So I generally change it back and forth, make sure that I have the right thing. Now, what this is going to do is going to create a density, temperature, and velocity field. And right now we don't have any geometry. We have only inputs. So we need to change this build SDF from geometry to stem points. And now we have our volume. Now you can see the volume is too thick, and we can change that by increasing the by lowering the sample distance, and that will make each voxel sample less points, the closer point to it, which will make it thinner. And this is our volume representation. I'm going to increase the resolution here to see it better. As you can see now, we have something a very thin volume surrounding the geometry. So just to 8.5. Okay, cool. Now we can also add noise to this, which is already there. So let's work on it a little bit more. I want to make it more obvious. I want to create more gaps into this. So I'm going to increase the turbulence influence, something like that. And then we want this to animate, which is the default behavior. So right now it's animating. I want to increase that a little bit. So let's lower the pulse duration. which will make it move faster, make the noise move faster. And I want to lower the element size. I want to make it smaller. Cool, something like that. And I was changing every frame so we get different emission every frame. And that's it. We also have temperature, so we need to be aware of that. And for the velocity, we haven't created anything because it's trying to stamp a v value, which we haven't created yet. And we didn't initialize any value. So we're going to leave it at that. And I'm going to create a null and call this out density. And now we're going to create a DOP network. And let's call this sim. Let's give it a red color. And let's dive inside. Now, the first thing we need is we need a smoke solver. We need a smoke object. And then to source the data from DOPs, we need to use a source volume node. And this works in conjunction with the fluid source node. Basically, it has a list of what you want to source inside the sim. It can be used for all kinds of purposes, for sourcing flip, for sourcing pyro, for sourcing pump forces, anything really. So the way it works, we're going to connect the smoke object first, and then the last one is the source smoke. And let's browse for the out density. And then for the smoke object, we need to select it, hit enter, and then we need to increase the bound so it covers the tank size. Okay, and let's hit play. Cool, so we have our smoke being emitted, and we'll probably see some rising of the smoke because there is temperature being emitted. So let's increase this to 50. You can see the smoke goes up more, and again because we have temperature. So in the next video we're going to start adding the force to push all of this, and once we have the setup going, we're going to start tweaking certain values to make it look a bit more interesting. Thank you for watching, and see you in the next video. Bye bye.